Once again, good evening, everyone. Now I'll be taking the module 8 of this program, Systems Engineering and Application, right? And in this module 8, I'll be talking about design structure metrics, basically the task dependencies, right? How the tasks are dependent or which kind of dependencies exist, and how do we address this in the systems engineering domain. So the topic is design structure metrics. If you remember in the last class, I was talking about system dynamics modeling. There again, we were trying to identify the cause and the linkages between the activities and what kind of cyclic feedback loops are there. And in the models, mathematical relations were involved. And based on that, we were trying to identify the polarity of the relations. Today, we are going to organize those identified system elements, right? So identifying system elements we did yesterday. Now the next step ahead or next requirement is there are multiple elements, multiple components, subcomponents, right? So now it becomes very important for us to understand that how these tasks should be performed, right? So once we got the relationships to simulation to system dynamics modeling, we are into the new question that how do we resolve or how do we manage these tasks or elements or subsystems in particular system. So types of systems and architecture. So the very first question comes up is systems architecture, right? I think in the module 2 or maybe after that, Professor Pandey might have covered this systems architecture. Systems architecture is basically the design of the system, right? That what are the subsystems, what are the components, and how they are related. The structure of the whole system will be called, usually called the systems architecture. Now, systems can be any, right? Organization can be a system. Multiple types of system exist. Except engineered systems, there are multiple kind of systems exist in the society or in the social context as well, right? So all the technical and non-technical institutes or organizations or setups may be forming a system, right? So let us see that what types of systems exist. So there may be product. Product can be behaving in system, then organization or process. So these three are the major ones. Depending on the context, there may be some more systems, right? So we'll be studying three major ones. These are suggested by Pinger and Browning, right? So to address these systems, it becomes very important for us to identify structure, the interrelationship of all the system components, right? So when we are talking about architecture, it means what is there in the inside structure of a system. So if I try to see what is there in the product structure or product architecture, we'll see subsystems, components, and functions, or there may be some more things you may list down based on experience. This gathers together, and when we arrange or order all these things in a systematic and logical manner, then we say it is the product architecture. Similarly, if I talk about organization systems, you see, this organization is made up of sections, teams, individuals, and then you may put some more, things if you want. Sections means departments, different, HR department, then finance department, then the salary section, then the sanitization section, the many different departments may be there in an organization, right? So when we systematically design or align all these departments, people, team, then we say it is the organization architecture, right? It's an organization architecture. So now the third part, the process, if I go to understand how a process architecture works, so I'll say that process includes different activities, different tasks, different parameters, right? And then it will be resulting into the process architecture, right? So after having all these things, product, organization, and process, then it becomes a question mark that do I need to manage it separately, these architecture are separate or not. So then I'll make a comment here that in an organization there can be a product, there can be the teams, there can be the processes. So when we combine all these three systems or system architectures, then we say we can get the multi-domain matrix architecture, right? So usually, in order to study the different aspects, you cannot, align everything together. So we divide the systems also in some parts in such a way so that that particular subsystem can be studied properly. So in order to study the product structure, there may be a dedicated systems engineer, and that fellow will be managing the whole product architecture particularly. Then there may be a separate team or separate systems engineer may be there who are talking about the organization architecture, right? And then there will be a third component, the process architecture. There will be again some separate systems engineer and separate teams who are working on the process architecture. So it becomes a very humongous task to develop the system architecture for the whole all things together, multiple things together, right? So in order to simplify the process, we divide that into the product, process, and organization or people related architecture, right? So this is how we talk about that how the things are there and in what manner they are related, right? So this is how the types of systems and architecture can be defined. So this will be useful to you. Let us say if some of you are working in a product, even in the product architecture also, you may have many, subsystems. By applying the system of system concept, I hope you might have studied it so far. Yes. So by applying the system of system concept, you may again further divide a product system into several subsystems. And then you may analyzing each subsystem separately, and then you may combine it to bring the product architecture together. So depending on the quantum of work, right? Depending on the required insights, you may divide the work in that manner. So here also I've divided in three segments, and then we'll see that how things are happening. Okay. So you may add more dimensions to these architectures. So now the question comes, okay, fine, we are talking about architectures. We'll be designing in a logical way how they are, getting performed in that particular system. So now we'll talking about types of dependencies. The first one, which is very common to many of you, some of you I have already taught, this project management. So in that you must have studied that what are the parallel tasks. Very easy to understand. Parallel means they are independent, and those tasks can be started anytime, right? And or you can say that both can be initiated at the same time, right? So this we'll say the independent task. So like this we represent, you see, in this with the start node, with the start node, they're starting, it means some they are independent. A start I put up to replicate it with the network diagrams. Okay. Start is just the initial point, and these x1 and x2 are originating from the initial point. They're independent. They're x1 and x2 both are independent of each other and happening at the same time in the process, right? And then you see further they may be giving information to other subcomponents or other tasks or other subsystems, right? So here the important point to notice is how the information flow is occurring. So you see, information is not get because x1 x2 are connected with the start node. They are not dependent on anything for the information. They're self-sufficient tasks or subsystems, but they are giving the output. Their output, let us say x1 is a subsystem. After completing that particular subsystem, the connection or the output of that particular system will be behaving as an input to another system, right? So this is how x1 or x2 are called the parallel task, independent task, but they play a role in providing information. So they play the role in the information flows, right? Similarly, there is one more task that is called, that you call the sequential task. That is also very simple to understand. Tasks which are related, dependent tasks, right? One will finish, then only the next will be started. So here you see x3 and x4 have been shown here. X3 is giving information to x4 and x4 is further releasing some information to upcoming activities or upcoming subsystems in the network or in the architecture, right? So here you see x3 is the predecessor while x4 is the successor. Predecessor and successor is something which is giving the information and which is receiving the information. So if I am saying x3 is the predecessor to x4, it means x3 is providing information to x4 and x4 is receiving information from x3. So x4 is becoming the successor. So if I say when you are having a sequential task, so we categorize into two parts. One is what are the predecessors and what are the successors. This helps us to understand or to identify that this particular activity is depending on what other activities, or depending for what? For information, right? So what information is required to receive in order to perform X4, right? So I'll immediately know that X4 requires information from X3. So it is very clear that X3 should be completed first, so that whatever is the output or outcome of the X3, that will be behaving as an input to activity or subsystem X4, right? So now, based on these relationships or dependencies, we'll be able to identify that what should be the sequence of activities. So that concept we'll be utilizing in the design structure matrix. So the two types of dependencies you have seen so far. One is parallel, another is sequential. These two we have commonly seen in the network diagram of project management. Remember the precedence diagram in the project management, and there we talk about this. But there is one very important thing that exists in the case of real systems, that after getting processed by some x3, x4 took the information, x4 processed it, and there could be a possibility that after processing at x4, there may be some information which is going back to x3. That kind of relationships are called cyclic tasks or coupled tasks, right? So these are interdependent. So far we have seen the dependency, sequential or parallel, but here you see both two or maybe multiple tasks may be interrelated. Input is going back to the originator of the information. So you see here in this particular, particular figure, you see that x5 is giving information to x6, and after processing that information or utilizing that information, some output have been developed, and that output information is again going back to x5. So this is how these X5 and X6 are called the interdependent task, or you can say the iterative task. Keep on processing and keep on sharing the information to and fro, right? So you see the one more cyclic task example is here. X7, X8 and X9. X7 is giving information to X9, right? And then X8 is receiving information from X9, and again X8 is giving information to X7. So basically, the information which originated from X7 is now further processed by X9, then further processed by X8, and then the output information is again going back to X7. So these kind of cyclic task dependency is also one of the very important phenomena which occurs in reality, right? So though in many of the cases, we see that it is not that common, especially in the precedence diagram, network diagrams. You must have seen that only two types of tasks we mention here. But if you try to put this cyclic task in the network diagram, it may not be responding. You'll not be able to set up properly, right? Many people feel that this dependencies or the network diagram are same, but it's a myth. Network diagram is sequence is already provided to you. You just calculate the total time, right? You do not bother that which is to be done first or which is to be done last. The order is sequenced. You are just, bothered about the total time required or the dates of the activities which are listed. But it is the fundamental thing. In design structure matrix, we'll be talking about not only the dependencies, but rather arranging them in the order. So you can say that prior to the precedence diagramming, we can do the design structure matrix. We can develop the sequence of, so the input to this network diagrams can be developed through DSM. We arrange, we sequence all the activities, we'll find out the dependencies and we'll arrange in the optimal way. Then only we'll be able to develop the further network diagrams. So in DSM, you will see that we'll be breaking the loops, minimizing the interdependencies. We'll arrange in such a way that interdependencies or feedbacks may be minimized, right? So that optimization we do, that rearrangement of the activities we do in the DSM. So here you see the limitation. In the precedence diagram, we usually have, activity A to B, that is finish to start. When activity A will be finishing, then only B will be started, right? Then the second type of relation of the activities are start to start. They both will start together. They're dependent. One will start, so at the same time, second will also start. They're connected. Then finish to finish means when activity A will be finishing, at the same time B will be finished. For example, if I'm saying the last class is over today, so with the completion of the last class, the whole course will be completed, right? So the completion of classes is dependent on the completion of the course. So both will be finishing together at the same time. The moment you declare the last class is over, at the same time you will declare the total course is also completed, right? That is called the finish to finish. Start to start means, again, same example. If I say today the day one of the class is started today, immediately I'll say the course is also started today, right? So this is how there could be several examples you can find out around you and around the product development when you will be doing some lab work or some experiments, right? Then the last one is start to finish. One is starting, another is finishing. So again, one professor finished the lectures, then only the next professor can teach, right? So one is starting, the other activity must be finished. So that is the start to finish relationship, right? Or you can say there is example of network diagram here, where the activities are having the this kind of finish to start relationship in this network diagram. But the limitation is that we cannot represent the coupled relationships or coupled linkages, right? So this is how it is the limitation of the precedence diagrams which we usually follow in project management, right? However, there are ways to express this coupled links or the interdependent task in the structure matrix or structure architecture. The important point here is to notify that many tasks happen in reality which are interdependent, right? And we cannot ignore that, especially when we are talking about the bigger systems, right? There are multiple things which are interrelated or interdependent. And to address those things, the design structure matrix is suggested, right? So design structure matrix is mainly suggested by Don Stewart in 1970s. Then Appinger and Browning took this concept and elaborated this in different forums. The book written by Appinger and Browning is full of use cases, right? The use cases defined by them are really very interesting, and they have showcased that how the DSM can be applied in the different system context, in the organization systems, in the product systems, or in the process systems, or in the multi-domain systems, right? So they have given multiple use cases, and that really is a very thorough book to understand the application of DSM in the industry, right? So DSM is basically commonly known as design or dependency structure matrix. So DSM helps in managing the complex systems architecture. It not only it helps in identifying the components and subsystems. Rather than that, it defines the interrelationships, right? And when you know the dependencies, as we have seen in the system dynamics modeling, right? We develop the causality, whether it is positively related, negatively related, or related or not, right? So all those hypotheses you can test very easily in DSM. After developing the dependency structure or dependency chart, it becomes very important for us to order or arrange the activities in a sequence. So DSM basically talks about that how the system should be, the architecture should be developed, what subsystems, tasks, or components which are required to be processed at the first hierarchical level, then the second, or then the third, or which is at the least. So basically, DSM helps us to develop a hierarchical structure of the subsystems, components, or maybe many other tasks and activities, right? So you see, DSM-based methods have demonstrated immense potential in understanding, creating, and refining complex system designs. It may include any of the systems which we have seen, maybe an organization, maybe processes and products. Then you see DSM consists of all components, subsystem, activities, and mention the information exchanges in form of metrics, right? So in form of metrics, what I mean, design is very clear. Design structure matrix itself is stating that what does it mean? It is designing the structure in form of matrix. Structure of what? Any system, because definitely we are studying in the context of systems engineering. So design structure metrics, the name itself suggests that DSM methodology helps you to create the structure or design the structure, and that we'll be doing in form of matrix, mathematical matrix, in the way you have studied in linear algebra. Matrix are having a very important role in engineering. Several methods are there where we utilize the matrix, especially in the decision making things, right? Here also you see when we are trying to uncover the structural relationship, or when we are trying to arrange all these activities and subsystems and the processes in a logical way, so that it can be an optimal sequence or hierarchical structure. This again we are making a decision only, right? So matrix is always having a very important role in designing or making any decisions in the systems. So now you see this DSM represents linkage between system elements in a square matrix, right? Then role of DSM in systems engineering. As I already told you that DSM is basically helps, or DSM is a kind of matrix, right, which helps us to understand, to uncover the relations and to develop the hierarchy. So here you see in systems engineering, DSM serves as a visual aid. Visually, you can see within the matrix that how things are related, right? This illustrates the complex connections and interdependencies among various components of a system, right? Then you see DSM's visual format. Why I'm continuously saying visual format? Because there is a matrix, square matrix, right? And in that we'll be marking out the dependencies. So easily you can locate that which activity or which task is dependent on which task, right? So that dependencies you may immediately locate by just visually seeing in the matrix. So DSM's visual format facilitates the communication of system dependencies and structure to all the team members, to all the stakeholders, so that accordingly they may plan that where I have to start or where my subsystems component will be ready to work on. Or you can say the system, no, this DSM or design structure matrix expresses the position of my work. Then from where I am receiving the information and to whom I am giving the information, to a particular team or to a particular subsystem. Subsystems are also driven by the teams only, right? Let us say electrical subsystems, mechanical subsystems, software systems. So definitely there are dedicated people who are managing these subsystems, right? So those people, they will understand that with whom I need to integrate so that I can get the required information in order to process my subsystems task, right? So this design structure matrix actually facilitates the communication of system dependencies, and with that, it helps to understand the collaborative teams also. That with which team shall I work? Because I need information from electrical subsystems, so I need to work with the electrical team members or stakeholders, right? This is how the DSM helps in multiple things. So further, it helps engineers to understand the systems architecture, right? Systems architecture, then critical interactions. What do you mean by critical interactions? You can say the feedback loops or cyclicity, if it is existing, it means it is little critical. How? For example, let us say X3, I mean the way I've shown in the network diagram, there is a activity X3 which is depending on X2, right? Now X2 is required to be completed in advance, right? Then only the X3 can be started because X3 needs the information from X2. If this logically arrangement is missed out, right? So what will I say? For the time being, just take it as an example that let us say X3 has been listed at the top of the work. That X3 you finish first, then later on somewhere X2 will be completed. So now just imagine, let us say X3 is completed, right? But it is dependent on X2. So now later on, let us say after 1 week, when X2 is processed, after processing X2, the information which is working as an output, that is going as an input to X2. And after that input, what will happen? You've already performed X3, right? So the input coming from X2 now after 1 week, what will it call? It may need to rework on X3 because X2 you have completed just now after 1 week, right? So this is how the information dependency is very important to notify while defining the. So what do we try? We try to minimize the rework basically. So the main agenda of design structure matrix is to create the clusters to break the feedback loops. We will see later that you see. So these activities may become critical, right? These interactions may become critical and you cannot ignore, right? So that is the reason why we will be going ahead. So further, if you see, it helps engineers to understand the system's architecture, identify critical interactions, and make optimal design decisions. Optimal design decisions, as I already explained, to minimize this rework, right? So when you are doing rework, what is happening? Extra efforts, extra time, extra resources, right? Resources includes the efforts, human efforts, and the raw material, and the other resources, electricity, and the machines, and many other things may be there, right? So when you are reworking on some particular activity, it clearly explains that it is not optimized. We don't want to increase any kind of cost or any kind of resource consumption, and this will help to improve the overall system and the overall integration strategies in a system. By the DSM methodology, we can easily break down a system into smaller parts. And when you have the smaller parts, or you can say the manageable, doable components, right? So then you may have a particular dedicated subsystems and the systems engineer for that particular subsystem so that you may identify the requirement of each subsystem separately and then you may link later, right? So this is how you can reassemble later on, and then this is how you will be able to get the better insights of all the subsystems involved in a system, right? So importance of DSM. Though we have already discussed a lot about importance, anyway, it helps in identifying the feedback loop. Identification of feedback loop is the critical task, or it is little complex to identify, right? Then it is used to optimize job sequences to to achieve a optimal arrangement so that the rework can be minimized. It visualizes the system complexity very easily. When you develop the matrix, you will immediately identify that what activities are depending on which other system, subsystem, or any other entity, right? So visually, you will be able to see that how complex it is. You can imagine the complexity of a system. Let us say a huge system, aircraft systems. I'm so sorry. I keep giving the examples of aircraft systems. Hmm? In yesterday's class, also, I spoken one thing about systems. The system you know the most, you will be able to understand it best, and then only you will be the better person to make the decisions. If let us say you are electrical engineer, right? And if I ask you to manage a software system, you need to give a lot of efforts. You need to study a lot, right? Because you know the software system less, you know the electrical system more. But if I ask you to develop the dependencies and develop the hierarchical list of activities which you can perform in an electrical system, it may become very easy for you because you know the system in detail. Those 4 years you have given during your BTech days to understand that electrical systems, right? So this is how the more you know about a system, the better decisions you will be able to make, right? So this DSM actually groups the components which interact significantly, and basically it will help you to plan the modular architectures. Modular architecture means simplified or broken down into the small pieces, and then you may reassemble together, right? So this is how it helps in project planning also. Though the precedence diagram and the network diagrams express the sequential and parallel activities, but in reality, there can be feedbacks also, feedback loops also, right? So in that case, the DSM may help to plan the projects effectively. Applications of design structure metrics. So the very first thing which I've already told you, that it is the arrangement of the activities, identifying the dependencies. So that is the main insight of the system, right? So this design structure matrix supports the change management in businesses. That's the very important thing to discuss here. Change management in businesses. Let us say some particular subsystem or component is required to be upgraded. Upgraded in the sense, let us say I would like to change some particular point, or you can say I would like to add some sensors. So immediately I have a proper map with me. I have a proper matrix where I am able to see that what are the list of subsystems, activities, components, and I know the dependencies also in the matrix cells, right? So when I am aware of these things in advance, and if I'm going to make a small change, just I'm taking a piece out of that matrix, so I know that what information I am losing, or what kind of changes do I need to make in the whole system architecture, or whatever information is getting developed by this added sensors, where it can be connected as an input, right? So one change you have added sensors, so there is a possibility that you need to add some more modules or some more dependencies may be generated. So this kind of design structure matrix, when you have all the things visually in your hand, it becomes very easy to understand that how you are developing this or managing the change in the business. Then effective project planning, that you already know. It specifies the sequence, structure, and interrelationship of the task or subsystems in the whole process of system. Optimization of process designs, right? When you know the sequence or the hierarchical relationship, right? What which activities to be done first and then second, and then after identifying that hierarchical structure, it will be easy for us or for you to optimize the process designs. Then the possible alternates, let us say two subsystems are deleted, right? So immediately design structure matrix may help you to reorganize the remaining activities, right? So that will immediately help you to report a particular arrangement in the design structure matrix, or you can say in the systems architecture, right? So let us say due to some reason some activity got delayed. It's possible in reality, it may happen many times. So when these kind of activities or when some, because everything never goes in favor, there may be mixed kind of things happen in reality. Some things may happen in time, some things are not working well, right? So when these kind of scenarios are there and you are now worried that my work, because I am from a different subsystem, let us say I'm from the electrical subsystem, and then some other fellow who is belonging to the mechanical subsystem, and my triggers, or you can say my system is dependent on the inputs provided by the mechanical subsystem. And somehow I am waiting and the mechanical people are not performing. The work got delayed. So definitely it will be pushing my work also. So in that case, there may be a requirement of alternate arrangements, right? So that alternate arrangements following the optimality also can be done by using the design structure matrix. Now you see this is an example of design structure. This is just a matrix though, right? You see this is a square matrix, right? So design in the design structure matrix, it's always a square matrix. Means the list of subsystems or components you are listed down in this, you see here X, Y, Z, and W. These are the list of sub activities or components. On the column side also you have to mention the same subsystems. And now the cells which are shown here, right, will be following or will be expressing the relationship. Let us say it is blank in this case. X and X are not at all related. Why? Because how can they be dependent? So I am just putting the cross in this cell. Right? So X cannot be taking any information from X. So I'm just putting the blank, the diagonal will be blank, or you can say when you process the matrix, you can say you can replace this diagonal with the zero values, right? And then one important thing to notice here, you see, there is a stars. There are stars which are marked in this particular, different cells. How do we read it? What information do I get from this matrix? So the first information is, you see, X is getting information from Y. So the row side, or you can say this row, if you see these are the rows, right? These are behaving as a successor or information receiver, right? While on the column side, you see these are the predecessor or information provider, right? So here in this case, when there is a star, it means X and Y are dependent. And how they are dependent? X is receiving information from Y, or X is having the predecessor Y, right? X depends on Y. X is information receiver or successor, and Y is the predecessor to X, right? Then again, you see the next cell. There is a star mark. Y and Z are related. Clear. How? Y is receiving the information from Z. Y is the successor to Z. Or you can say Z is the information provider, right? And Z is providing the information to Y. Or you can say Z is the predecessor to Y, right? Then the third cell, if you see, it is Z and W are related. So when Z and W are related, you see, again, Z is the information receiver and W is the information provider. So I should say W is the predecessor to Z, or the other another way I'll say Z depends on W to receive the information. In the last cell, or you can say the row belonging to W, W is not related to Y, Z and W itself, but related to X only. In what sense? When W is receiving information from X, right? And X is the predecessor to W, right? So this is how W depends on X. And you see, X, Y, Z and W are creating a loop. How? The important point to notify here. X depends on Y, then Y depends on Z, Z depends on W, W depends on again on X. So there is a cyclic feedback which exists in this task structure matrix, right? So you see, in this design structure matrix, this is just a matrix. Further, we'll process it, right? Through design structure matrix steps, following some linear algebraic steps about the matrix, and then we'll get the details about the components and the relationships. So here you see the same set of system items are represented using rows and columns the way I've done here. Rows and columns are having the same names. This is how it becomes a square matrix, right? Then you see cell represents the relationship between two elements. If it is blank, you see it is mentioned. Star indicates an interaction between elements, row elements and the column elements. If there is a relationship, we put it as 1. If no, it is 0, right? Diagonal elements are basically the elements or cells which are expressing the interdependencies on on itself, which is can be expressed as zeros, right? Now, one important thing to notice here: X, Y, Z, and W are there. If nice, but here you see X is trying to receive information from Y, right? So this is how it is very clear from this particular matrix that X is depending on Y. And you see the sequence here, the order here. Order is saying that X to be processed first. After that, Y should and Z and W should be processed. But if you see little closely, X is dependent on Y. So without receiving the information from Y, if you process X, what will happen? Yes, what may happen? What problems you may face? Very clearly mentioned here. X will be on the top, X will be done first, then Y will be done. So when X you perform, though X requires input from Y, and now you are performing Y later. So when Y will be finished, then only that information which is being processed from Y, then only it will again going back to X. So once you already performed X, now a piece of information you received again. So don't you think that it is calling for more and more reworks? Yes or no? Right? So these are the glitches that can be addressed very easily in the design structure matrix. So if you keep on looking into it, again, y is dependent on z. You see in the second row, y is dependent on z. It means, and y is listed on the second level or at the second priority of the task, list of tasks. And now if you finish y, then again you may be getting information when z will be processed. So piece of information you will receive when z will be completed. So then again our information input you will be receiving from z. Then what will happen? Rework of y. Now again reworking on y. Again some information change may there, and x will again impact it. So that is how this cyclic loop will be keep on happening. Then along with the information cycle, there will be one more cycle of rework. Yes or no? And that rework sometime may result into scrapping the work completely. There could be a possibility that then without that information, whatever you have done, it is all waste. Right? So it is not only rework, it will be the huge consumption of resources as well. So that are the issues which we face in reality. And in order to minimize those problems, it becomes very important to develop the system architecture very intelligently and logically so that it can be completed in an optimized way, right? So that's the major takeaway of this particular um, design structure matrix, right? Or the task dependencies, right? So now you see what are the steps to follow in design structure matrix. Now it becomes very, very urgent that okay, fine, it is all truly decided or it is well defined that there is a need of structuring the subsystems, components, as tasks logically so that this rework can be minimized. It is very clear by now. Now, how? So, the very first step is develop a square matrix with the system elements on rows and columns so that you will be able to define the interdependencies or dependencies, right? Then, in the second step, mark the dependencies as we have seen in previous example, right? After now, the question may be that how do I mark the dependencies? How do I list the system elements? So those who are the researchers here, for them it is very important. See, as I told you that the system you know the most, you will be able to address the things better. But for example, let us say you are a researcher, you are just trying to, yesterday I gave you an example of food supply chain, right? A similar example I'm taking. Let us say you are a researcher, you are the student of industry engineering department, and you would like to understand the food supply chain. What are the elements? What are the how they are dependent on each other? What are the which suppliers are depending on supply of any other supplier or vendors? So like that you will be or on what raw material they are dependent on multiple people. So likewise, we all try to bring the insights about the food supply chains, right? And then there become a question mark that how will I list the system elements because I'm not into that system. So these things you can have from literature review, from the expertise and the experienced people who are involved in those particular system. Right? So those who know the system most, they will be the right fellows to tell you the system elements and system components along with its dependency as well. So this information you may gather from literature, research papers, books, and from the people who are working on the domain. Then the next step is sequencing. So now when I'm saying sequencing, see the two statements are popping up. Move empty rows to the top. What do you mean by empty row in a matrix, especially in the case of square matrix? Empty row means that particular component is not depending on any of the listed subsystems or components. Or you can say this particular component is basically independent. It does not require any information from any other elements of the system listed here. So can we push it towards the start node? Start node means top of the matrix structure, or start node means initial, or it can be done at very first because it doesn't need any information, right? So those rows which are empty, it means this particular element is not depending on any other subsystems or subcomponents, right? So it can be very easily moved to top or upside on the matrix. So you see, we are just sequencing, right? Then one more statement is mentioned here. Empty columns. What do you mean by empty columns? What interpretation can be made? Empty column means this particular element is not giving information to any of the components or subsystems listed in this particular system. It means that component is not providing information to anyone. To shift it towards the end node, or it can be last in the hierarchy because no activity requires information from this, or none of the components of the system depends on the information of this particular component. So it can be moved towards the end, or you can say that column should be shifted to the right hand side, or you can say the closer towards the end node of the system, right? So this is how things can be defined. Okay, so the empty rows and empty column concept is now clear to you, I hope, right? It is again the same concept, whether this activity is the predecessor to anyone or the successor to anyone. If no, put it towards the start node or towards the end node, right? Any doubts in it? Yes. Yes. Similar to, in the network diagram, what do we say? The activities which are independent are towards the start node, right? And those activities which are not giving information to anyone will merge to the end node. So similar to that, we'll try to rearrange the sequence of the activities, because usually you may get the system elements, but the sequence is very difficult to receive, right? So that sequencing or that optimization concepts will be applying here. So the next step is pairing. Pairing is something, you see in the previous example when we were, following this, you see, these are called the pairs. Pairs in the sense, again, blocking the diagonals, one, two, three, and then last the fourth pair. So now you see these are called the tears. This is a tear. This is called the tear marks, and which we try to avoid. Why? Why we would like to avoid the tears? So removing these tears is called tearing. All these points, see, if I arrange these activities, though it is shown that X should be done first, then Y, then Z, then W. This sequence is defined. But as I already explained that X is dependent on Y, so there will be a feedback loop keep going on. And as soon as you finish X, or as soon as you finish Y, again some information is going to back to X, and then again you will redo X, right? As soon as Z will be finished, again Y will be reworked, again Y reworked, then the information will be again rectified for X. So this is how that cycle will be keep going on. So in order to minimize it, if you see logically, X is dependent on Y. So it is very clearly shown that Y should be done first, right? And Y is dependent on Z. So Z should be done prior to Y. And Z is dependent on W. So W should be performed before Y, right? So this is how these kind of things are there always in the system. And we try to minimize the rework. And in order to minimize the rework, we just try to understand that what should be the correct order. So here we will try to remove the pairs. In order to remove the marks above the diagonal. So all those marks which are above the diagonals are not favorable. So the target of DSM is to break down those feedback loops, right? So these marks which are these dependencies which are shown above the diagonal are actually representing the feedback loops. And this design structure matrix, the purpose of this design structure matrix is to reduce down these feedback loops. They break that particular works which are interdependent cyclically into smaller pieces so that the extra rework can be optimized, right? So here you see in the pairing step, what do? We identify the task if the dependencies on other activities. Later activities should be preferred. It means, let us say X is dependent on W. So that relation we'll try to discover or uncover first. And those particular things will be, or those rows will be moved towards the top, right? And this particular pairing step is an iterative step basically, right? And the target is to break down all those tiers or all those feedback or cyclic loops so that the activities can be broken down in smaller pieces to avoid this feedback loops, right? So the agenda is to bring all the dependencies below the diagonal. Below the diagonal says the sequence is arranged in such a way that the further activity or the later activity is not dependent on the, the initial activity is not dependent on the later activity, right? So this is how the pairing step will be, iterative step will be performed. And in every iteration, the dependencies which are above the diagonal will be located, and then those rows, corresponding rows will be moved towards top so that they can be completed first, and then the later activities will be assigned, right? And a point will come that most of the dependencies may come below the diagonal, or you can say very close to the diagonal, right? There could be a possibility that you cannot completely remove all the interdependencies. So in that cases, we'll just try to bring it closer to the diagonal. And then the next step will be the banding. Banding expresses the independent activities with different colors, right? And then it helps to identify the crucial activities. So those activities which are having different kind of dependencies will be expressed in a different color. So it will be easy for you to understand that what are the independent activities and what are the crucial or critical activities. Then the clustering. Clustering is very important thing. Then though you have seen, you minimize the interdependencies, you rearrange the hierarchical structure of all the activities, which is to be done first, which is to be done last. That can be done using DSM. Then the next thing is clustering. Clustering means, if you remember, I was giving an example. Let us say for some electrical subsystem is dependent on software system or mechanical subsystem, right? So if this dependency is there, it means I know that I need information from software system or from mechanical system. So I will work closely with those two subsystems, right? So this is called clustering, that the electrical system will be working closely with the software subsystems teams, or we are just monitoring, we are working together hand in hand, receiving the information, processing it, giving it back. So that kind of clustering is also required, because this is also part of optimization, right? Because the information which is required to receive from one subsystem is to be used, and at what time exactly that information is required, when and how to process. So to process it completely, it becomes very important to closely work together, right? So the electrical subsystems team will be working closely with the software system team, right? So that is called the clustering, grouping the highly interconnected elements which are less connected to the rest of the system, right? So that becomes very important for teams, for the subsystems or systems engineers who are working around, right? So that is also an important insight to optimize the whole systems. So this is one more example. You see, these are the, this is the task structure where the sequence is mentioned, task IDs are mentioned, activities names are mentioned, and then the dependencies are mentioned. So if I would like to show it in a matrix, it should be looking like this. So these dots, the black, these black points are actually these, you see, these points, these black dots are expressing the dependency, right? This is just a visualization. So now it is very clear that task ID 1, that is design fuselage, is dependent on the 10th task or 10th ID, which is requirements detail, right? It is very clearly mentioned. So we know in advance that these are the dependencies. But the sequence which is mentioned here, so two things which I got. One is a list of components or list of activities. The second is the dependency. Now my objective is to process this matrix information so that the sequence of the activities can be rearranged, or the sequencing, the banding and the clustering can be done to bring out more insightful decisions. So now let us see what does it mean. It means that design fuselage is depending on the 10th activity, which is listed after 9 activities. It means you are processing the task ID 1 now, which is dependent on 10th activity which you will be doing after finishing the 9 activities. So how meaningful it is? Hmm? Is there any meaning? I don't think that is there any meaning. Do you feel it? You are doing one thing now which is dependent on the things which you will be doing after 9 activities or 9 subsystems or 9 components. So is there any point to process task ID even now? We'll do it after finishing the 10th activity only, right? So this is how, though it is very small list of set or a small list of components, just 11 activities. But in reality, how many activities happen in reality? If you see just an electrical subsystem, even then there may be at least 500 to 800 activities, or more than 500 elements may require. It's an electrical subsystem of an aircraft system, right? Instead of hundreds, it should be reached to thousands, right? So now imagine when there are 1,000 components list with you. Here it is very easy to do. You can immediately find out that one is dependent on 10, so put the one after 10. When then will be finished, then only one will be performed. It is very easy to diagnose and analyze, and you may just do it on pen and paper, and that will be good enough. But imagine when there are more than 1500 or 2000 activities or components, and the multiple complex dependencies may be there. It is not just as clear you are, the half of the chart is blank here, but in reality, huge complexity may involve several. When you see 2000 activities are there, so minimum 1000 interdependencies and feedback loops must be there. So in that cases, how will you perform? How will you understand? It will be a mess. It will be a super complex engineered system, right? So then in that sense, we'll try to understand that how can we apply this using the computer based softwares, right? Or some particular computer based calculations, because it is not possible by humans to develop or rearrange this particular matrix, right? So that is how we follow the same steps which we have mentioned, and then you may write the algo to the to a software, and then you may develop the things in the computer software so that you can finish this task easily, right? So you see, this is the dependency sequence. Yes, I also use the software. Okay. So in this, you see the sequencing of the task is been done. And then in the next step, you see the clustering. Though it is a small subset of activities, the clusters are not very clearly coming up, right? But still, we'll be able to identify that some things should be working together. Some things should be, some things, you see, this dependency sequence is different. It has been restructured or reorganized to arrange the sequence of activities. Another insight in the DSM matrix is to understand that which teams or which subsystems should be closely working together. Though set just 11 activities, so it is not clearly coming up here. But still, you can see the pink lines. These may be working together, right? So this is how the clustering sequence may be organized to get the insight that how teams or how the subsystems should be working together. Right? So you see how these steps we have followed. We have sequenced. Empty rows have been moved to top. I hope you have noticed it. You see here. You see here the empty row is at the top and empty column. You see this row is empty. It was there earlier in the downside, but now after dependency sequence, it is, you see, it is the empty row which is on the top, and it is empty column which is on the corner, right? I think it is an iterative process, so it is just one iteration, because I just notify one thing here that there is one more empty row. So this iteration was required once again. The ninth column is also empty. So these two activities should be going towards the end, right? Because they are not giving information to any other activity. So this empty columns 11th and 9th should also be moved towards the right hand side of this matrix. So it is just first iteration to identify, to see that how things are working, right? How the rows are rearranging in order to decide the hierarchy of the structure or the system's architecture, right? Then you see these steps were followed, and accordingly you may perform it in any of the computer software. Then this is one more task structure. You see there are 30 activities listed, and the names are, the sequence are, so now you see here, this is the again a structure where the task IDs are mentioned, sequence of, this is from x1 to x30, the hierarchy structure which is random row is defined, right? And then the dependencies are defined. This is the input to a it is an input to a system. And now systems engineer will be the fellow who will be rearranging all these tasks or all these subsystems so that the work can be finished properly and in an optimized way. So in order to finish this, we will be listed down this particular activities, and you see this is the x1 to x30 are mentioned here in this matrix, right? So in this, the important point to notify all the sequence, the way it was given, it is mentioned the initial matrix, right? And this, circles, these black dots, these black solid dots are here, which are actually defining the dependencies, that the second activity is depending on first, then the third is depending on this one, third is depending on 28th activity, then the fourth activity is dependent on second, fifth activity is dependent on 16th activity. So now just imagine, is there any point to perform the fifth activity now when it is depending on the 16th activity, which is in the 16th sequence of the list, right? So some things which we can easily identify, but even this 30 by 30 matrix will be very difficult to solve manually. So you may take help from the softwares and get it done. But now the question mark is, what are the logics you will be writing or you will be giving to the software systems? So again, I'll be mentioning one thing, that move the rows to top or move the columns to the right. That that much but the mathematics behind it, right? So you have to give in the iterations, you have to write many set of you know programming, and where the linear algebra is the base, right? So all these matrix calculations can be performed using the mathematical expressions which you have studied in different other modules in this course, right? So that kind of expressions you may utilize to give the input to the software to process the input, or to perform the optimal sequences or optimal iterations in order to minimize the rework. Right? So let us see that how the next step would be. So you see the dependency sequence, first iteration of the dependency sequence, right? So in this, the first step has been done, that all the empty rows are at the top, right? So this is how it will be very easy for us to identify that how the things are rearranging. Okay. So after rearranging, you see in the dependency sequence things got arranged, and none of even just one point or one tear is left above the diagonal. Remaining all feedback dependencies are now moved towards the below the diagonal, right? So this is how all the dependencies have been moved towards the below side or the lower side of the diagonal, and that was the major requirement. Why and how, I've already explained. The more are the dependencies, especially on the later activities, it may not be able to support the optimized sequences, right? So this is how we always try to find out that what is the optimal way to complete the subsystems or other processes in a system. Then you see how beautifully the clusters are coming up here. In these clusters or the clustering sequence, you see the different pink squares are revealing. So these pink squares are actually showing that how these particular activity 30, you see, activity 30, 29 and 27 should be working together, should be closely working with each other. Similarly, activity 6, 3, 28 and 24, these are the one another cluster which should be working closely, and these are less related with the other activities. So this is the clustering sequence which you may get, right? Which helps the teams to work together, right? So with this, I would like to tell you that the linear algebra or the optimization algorithms you have studied in different other modules, you should apply those algos and the linear algebraic formulations to uncover the algorithms which are utilized in the design structure matrix. All the matrix calculation may be helpful, right? And this can be done through different softwares. One is MATLAB, which I've already explained, right? Other than MATLAB, you may use DSM Web to identify many other tools which are available over this DSM Web, right? Then as I already explained, that the Stewart's book, The Design Structure System, and his research paper published in 1981, it's very useful and very insightful discussion have been done in that particular research paper. Then the second is Eppinger and Browning books. The use cases of design structure metrics. These use cases are discussed in so much detail, right? And I'm sure that it will open up your mind to apply the DSM in multiple systems. And last, that is dsmweb.org. This in this website, all the possible resources, all the possible documents are available, which you can pursue to elaborate further. Because this is an introductory class, I mean the time is limited. I could not invest much time in this. So I think with some examples you will be able to do it on your own first, and then just following the algorithmic steps, you may mathematically write the codes and may be able to run it, especially over the MATLAB. MATLAB is the best tool, especially for the matrix. I hope you know about it, right? So please apply that and please practice. If you have any query, you may write to me or meet me before the next class. Thank you so much.